We now move on to the second half of chapter 17. In this part of in this section, we're going to be looking at solubility equilibria. You may recall way back from chapter 4 that there are certain compounds that have very low solubility in water, certain ionic compounds that have very low solubility in water, as compared to other things like sodium chloride and sodium bromide that have very high solubility in water. Well, we'll find that regardless of whether it is a low solubility substance or a high solubility substance, we can describe the solubility characteristics of an ionic compound using something we call a solubility product. We can write out an equilibrium equation, like for barium sulfate here. Barium, to the extent that it does dissolve, it does dissociate. It gives us barium ion and sulfate ion. Now, the solubility for this is very, very low, but there is some amount of solubility that we can measure with it. The way that we would describe this would be to use a solubility product constant, an equilibrium constant, and that equilibrium constant would look like this. KSP equals the concentration of barium ion times the concentration of the sulfate ion. This particular substance has a solubility product constant that is equal to 1.1 times 10 to the negative 10. We do have a whole table of these that I will show you here in just a moment. Let me show you another example of a solubility product. So here is for the dissolution of calcium phosphate. Well, calcium phosphate, because calcium has a 2+ charge and the phosphate has a 3+ charge, the way that we get a neutral compound is to have 3 of the calciums and 2 of the phosphates. That means that when, to the extent that it actually dissociates, we're going to get 3 calcium ions and 2 phosphate ions. Well, as far as the solubility product, because these have coefficients, that means that we're going to have exponents in our solubility product expression. So calcium will have an exponent of 3 because of the coefficient 3 here, and phosphate will have an exponent of 2 because of the coefficient 2 here. And you'll see there is the value, a very, very small number, but that is a measurable number. We can find these KSP values in Appendix D3. And so I'm going to show you Appendix D3 real quick. And so let me find it. There it is. So here is Appendix D3, and the barium phosphate that I showed you a minute ago, 1.1 times 10 to the negative 10, and calcium phosphate, or that was barium sulfate. Calcium phosphate here is 2.4. Oh, that's sulfate. Calcium phosphate, 2.0 times 10 to the negative 29. So you'll see lots and lots of different values here, and we're going to be doing some examples with these. Now, just as a note, solubility product is different than solubility. So solubility product is a different quantity than solubility. We'll use the word solubility to describe how much of a compound will dissolve in a given amount of solvent or solution. Typical units for solubility are going to be grams per liter, grams per milliliter, or moles per liter, or you could indicate that as molar. So that would be our units for solubility. If you have KSP, you can get the molar concentrations of the ions using a concentration table, which I'm going to show you how to do here in just a couple of minutes. And the molar solubility, here's the cool thing. When we do the ice table and we solve for X, X is the molar solubility. And with that molar solubility, we can go on to find the solubility in terms of mass in grams per liter. And if we want to, sometimes we can even get that in terms of grams per milliliter, just by using the conversion from liters to milliliters. Okay, so now what we want to do is I want to show you how to calculate solubility from KSP. So using our KSP values that we have on Appendix D3, how to find the solubility of a substance. So we're going to start with calcium fluoride. Calcium fluoride is a good example because we've got the number for it, and it's a pretty easy problem to set up. It also has a situation where we've got two of the fluoride ions, and that I like to show you this because that will affect the equilibrium constant expression. So here, if we want to find the solubility of calcium fluoride, we need to set up a solubility table, or a concentration table, an ice table, in other words. Our initial concentration, if this is in pure water, our initial concentration of calcium ion and fluoride ion would both be 0. So our initial concentration of calcium ion and fluoride ion are both 0. Because calcium fluoride itself is a solid, we leave it out of the expression, and therefore it will not show up. We'll just have dashes here in the table. We don't put numbers in there. So KSP is going to be equal to concentration of calcium ion times the concentration of fluoride ion squared. And if we look for this on Appendix D3, and I'm going to show you where we find this on Appendix D3. Here is calcium fluoride at 3.9 times 10 to the negative 11. So 3.9 times 10 to the negative 11, and that's where we get that particular quantity. Well, if we put these values in terms of x into the expression, for calcium, we put x. For fluoride, we put 2x. And then we get, and then of course we'll square it. This is something that sometimes students find a little bit strange, but we have 2x and we square it, but that's just how the math works. And so there, when we multiply all that out, we'll get 4x cubed. So now we've got a cubic equation. Fortunately, it's a very simple cubic equation that we can solve. So here is the x cubed is equal to that quantity, which you could punch that into your calculator. To take the cubed root on your calculator, there's a couple of different approaches to doing this. And I'm going to show you real quick how you do it on this particular calculator. And let me clear that out. So here we've got a math button, and the math button right down here, you will see on number 4, you can take the cubed root of something by doing that. So the cubed root is 3.9 times 10 to the negative 11. And we want to divide that quantity by 4 and put that in parentheses, and we get this, 2.1 times 10 to the negative 4. However, another way we can do this is, if you don't want to go digging into that menu, another way you can do this is the 3.9 times 10 to the negative 11, divide that by 4, but then raise that to the 1/3 power. So I'm going to raise it to the 3, and then the negative 1 here makes that 1/3, and you'll get the same quantity there. So if you raise it to the 1/3 power, that's the same as taking the cubed root. So I'm going to go back. And so here you can take it to the cubed root. The nice part about this is that you don't have to dig into the menus of your calculator to find it. And there we go, 2.1 times 10 to the negative 4 is that value. And just as a reminder, x is the molar solubility. So x is the molar solubility. Anytime I ask you for molar solubility, solve for x. So you're just trying to solve for x. And it doesn't matter what all these quantities are, you're just trying to solve for x. Okay, well, that is that kind of problem. Now, before we do one of those on the in-class assignment, I want to show you factors that affect solubility. And our most common factor that affects solubility is the common ion effect. We're quite familiar with the common ion effect. If we have a strong electrolyte that has an ion in common with a weak electrolyte, then it will affect the dissociation of that weak electrolyte. Well, here our strong electrolyte would be some sort of soluble ionic compound, like, I don't know, sodium fluoride is the example. And our weak electrolyte would be something that is very low solubility, like calcium fluoride. And so here, this shows how calcium fluoride, there's the number that we calculated a minute ago, 2.1 times 10 to the negative 4 in pure water. Well, if we add just a little bit of the fluoride ion concentration, if we increase the fluoride ion concentration ahead of time, then that solubility drops off pretty precipitously. Precipitous, that's kind of a joke there. Okay, so if one of the ions in the equilibrium is already there, the solubility goes way, way, way down. For calcium fluoride, we could either do calcium ions or fluoride ions to demonstrate this solubility decrease. So I'm going to show you both. So we'll start with calcium ion as the common ion. So here, calculate the solubility of calcium fluoride in 0.010 molar calcium nitrate. So calcium nitrate is a strong electrolyte. The solubility of this is the concentration of the calcium ion. Here is our equilibrium for our weak electrolyte. Remember, when you're using common ion effect, you write out the equilibrium for the weak electrolyte, and then the strong electrolyte is going to tell you what the initial value is for one of your ions. The ion here is calcium. It was 0.010, so 0.010 plus x, 0 plus 2x. We now have these values of x, and we're going to put that into this expression. So we'll have 3.9 times 10 to the negative 11 is equal to 0.010 plus x times 2x squared. Now, much like what we've done before, it is possible to neglect x, to say x is small compared to the value that we are adding it to or subtracting it from. In this case, we're adding it. And we saw as long as x is less than 5% of that quantity, we're good. And we will find it's definitely less than 5%. So we're going to neglect that x. After we neglect that x, we'll get 3.9 times 10 to the negative 11 is equal to 0.010 times 4x squared. Well, we're going to solve this for x squared, like that. So we'll divide both sides by 0.01 times and 4. And then we're going to take the square root. That one's pretty easy because most calculators just have a square root button. And we'll get 3.1 times 10 to the negative 5. Again, x is the molar solubility. So our molar solubility went from 2.1 times 10 to the negative 4 down to 3.1 times 10 to the negative 5. That is the common ion effect. It decreased the solubility of our weak electrolyte by having a strong electrolyte with an ion in common. So now I'm going to show you what happens if we use fluoride as the common ion. So here, if fluoride is our common ion, again, so here we're going to use sodium fluoride as the strong electrolyte. Here is our equilibrium. I've already described that. Our initial concentration of fluoride ion is going to start off at 0.010, and I chose the same concentration as I did for calcium on the previous thing, just to show you there's a difference in the overall solubility. So here we're going to have 0 plus x is x, 0.010 plus 2x is equal to 0.010 plus 2x, and then we will get so 3.9 times 10 to the negative 11 is equal to x times 0.010 plus 2x squared. Well, much like what we've been doing when we neglect x, we can also neglect 2x, right? If x is small compared to the thing we were adding it to, 2x is probably still small, and it turns out it definitely is. So here we are going to neglect 2x. And so we will get 3.9 times 10 to the negative 11 is equal to x times 0.010 squared. And so now we get this. So 3.9 times 10 to the negative 11 divided by 0.010 squared. And that gives us a value of x of 3.9 times 10 to the negative 7. Now I want to sum up the solubilities for the pure compound, the solubility for the compound in pure water, the solubility for the compound in 0.010 molar calcium ion. So you'll see it went down by about 1 order of magnitude. So that's a pretty big decrease in the solubility. And then also when we added fluoride ion, it went down even more. So instead of going down 1 order of magnitude, it went down 3 orders of magnitude. So that is a pretty significant decrease in the solubility. Okay, well, what we want to do now is we want to go over to our in-class assignment number 51, and switch over here. So the question, our very first question here is, use Appendix D to calculate the molar solubility of silver bromide in pure water. Well, so I'm going to write out the equilibrium constant expression up here. So KSP is, well, to do that, let's go ahead and write this. So silver bromide solid. Silver ion is a +1 charge, so silver ion is +1, and bromide ion is -1, so there is that. And the KSP is going to be equal to silver ion concentration times the bromide ion concentration. And we can use Appendix D. To get that value. So we'll look here. Silver bromide is right there, and it's 5.0 times 10 to the negative 13. So 5.0 times 10 to the negative 13. So I've written that number down here. So now what I want to do is I want to write out this expression again. So AgBr solid is in equilibrium with Ag plus Aq plus bromide ion Aq. And we're going to put an ICE table here, so ICE. For this, in pure water, our concentration of silver ion is 0. Our concentration of bromide ion, also 0. The change for silver will be plus X. For bromide, it will also be plus X. So this will give us X and X. Okay, since we know that KSP is 5.0 times 10 to the negative 13, we'll put 5.0 times 10 to the negative 13. And then here is the expression. So we're going to put X and X. So it'll be X squared. Well, this may be the easiest one we've done all semester, right? We're just going to take the square root of that quantity to give us our solubility. So we will do the square root of 5.0 times 10 to the negative 13. And we'll call that 7.1 times 10 to the negative 7. So X is 7.1 times 10 to the negative 7 molar. And as I mentioned earlier, that is the molar solubility. So that is the answer to this question. Again, if it's asking for molar solubility, you are looking for X. All right, so that was pretty easy. That was not too bad. So for our next one, since I've already got the equation written right here, I don't want to rewrite that equation. I'm just going to put the ICE table here. All right, so silver ion concentration in 0.030 molar silver nitrate. That silver ion concentration is going to be 0.030. For the bromide, the concentration of bromide in that solution is 0. This will be plus X, so 0.030 plus X, and this will also be plus X. So now we'll put this into the expression, and that will be 5.0 times 10 to the negative 13, is equal to 0.030 plus x times x. Now, of course, we could multiply that out, get a quadratic equation, use the quadratic formula, solve for x, and spend an extra 5 minutes doing this, but our simple choice for doing this is simply to neglect x. When we do that, we are saying that x is small compared to 0.030, and we will definitely find that that is the case. So that gives us 5.0 times 10 to the negative 13 is 0.030 times x. So x is equal to 5.0 times 10 to the negative 13 over 0.030. All right, and that's easy enough to figure out. It's going to come out to what, 1.7 times 10 to the negative 11, something like that. Let's go ahead and punch it in because we don't want to do that in our heads. No reason to do that. So times 10 to the negative 13, and we'll divide that by 0.030. So 1.7 times 10 to the negative 11. So we will see that our common ion effect, by having this 0.030 molar silver already present, that it decreased the solubility by about 4 orders of magnitude. So it went from 10 to the negative 7 down to 10 to the negative 11. That is a huge decrease in the solubility. So it's an absolutely huge decrease in the solubility. So finally, let's look at bromide here. So bromide. Again, I'm not going to rewrite the equation. I'm just going to put the ice table. So it applies to the equation that is right here. In sodium bromide, our concentration of silver is 0. In this sodium bromide, our concentration of bromide ion is 0.10. Again, these will both be plus x, so x, and 0.10 plus x. All right, so we'll put 5.0 times 10 to the negative 13 is equal to x times 0.10. All right, I messed that up. So 0.10 plus x. And just like we're getting used to doing, we are going to neglect x. And if you do this enough, you'll start having dreams about neglecting x. Maybe. Okay, so we get 5.0 times 10 to the negative 13 is equal to x times 0.10. X is 5.0 times 10 to the negative 13 over 0.10. Well, I can already tell that's simply going to be times 10 to the negative 12, but let's go ahead and put it in. 5.0 times 10 to the negative 13, and we will divide that by 0.10. And that gives us 5.0 times 10 to the negative 12 molar. All right, so 5.0 times 10 to the negative 12 molar. So in the second part of this problem, I know it seems like we just did 3 parts. Do we need a second part? Well, this one I've chosen it because it has a different coefficient here, and that means that will affect our equilibrium constant expressions. So let's go ahead and write out the equilibrium reaction for this. So PbI2 solid is in equilibrium with Pb2 plus AQ plus 2 iodide AQ. And we're going to put the concentration table directly beneath it. So I'm going to write the KSP right up here. So KSP is going to be equal to the concentration of the lead ion times the concentration of the iodide ion squared. And I've given you the KSP value here. I don't think this one is in your table. So I picked this one from a different table. So 9.8 times 10 to the negative 9. And that is our KSP value for lead iodide. So let's do our concentration table. In pure water, so we'll do initial change equilibrium, just like what we have been doing. In pure water, our concentration of lead, well, I hope it is 0. Our concentration of iodide, also 0. The lead, it will increase by X. Just as a reminder, whatever the coefficient of the chemical is, that's going to be the coefficient of X. Since this is 2 iodides, this will be plus 2X. And so now we will put these into this expression. So 9.8 times 10 to the negative 9 is equal to X times 2X squared. So X times 2X squared, if you multiply that out, the 2 gets squared, so that's 4, and then we'll have X squared times X is X cubed, so we'll have 4X cubed. If we solve that for X cubed, we're going to get X cubed is equal to 9.8 times 10 to the negative 9 over 4. So we'll need to punch that into our calculator and then take the cubed root to get our value for X. And we'll take the cubed root. All right, so 9.8 times 10 to the negative 9, and we want to divide that by 4. And we want to take the cubed root. So I'm just going to take I'm going to hit this button, and that'll pull up our answer. So I'll hit that and then raise it to the 1/3 power, and that's 1/3, and that's going to give us 1.3 times 10 to the negative 3 molar. So 1.3 times 10 to the negative 3 molar, that is our molar solubility of lead iodide. So that is our molar solubility of the lead iodide. Well, now we're going to do the same equilibrium, but now we're going to do it in lead. So our lead concentration. So ICE. Our initial concentration of lead is 0.010. So 0.010 plus X is 0.010 plus X. And then here, this one is 0 because there's no iodide there, plus 2X. And that gives us a 2X there. So we'll get, I'm going to draw a line here to separate these out. And we will get 9.8 times 10 to the negative 9 is equal to 0.010 plus X times 2X quantity squared. We're going to neglect that X. So neglect X. And when we do that, we get 9.8 times 10 to the negative 9 is 0.010 times 4X squared. So X squared. This is a lot like the one we did on that we did a few minutes ago on the overhead. So let's see. X squared is 9.8 times 10 to the negative 9 over 0.010 times 4. And that's going to give us a value for X. We'll just need to take that quantity and then take the square root. So we'll get 9.8 times 10 to the negative 9 divided by 0.01. And then we'll also divide that by 4. And now we need to take the square root. So we'll do second square root of our answer. And that gives us 4.9 times 10 to the negative 4 molar. So 4.9 times 10 to the negative 4 molar. Okay, so now let's look at initial change equilibrium. Initial change equilibrium. Here, our common ion is the iodide ion, so we've already got some of that iodide ion present. So our initial concentration of lead in there is going to be 0. Our initial concentration of iodide is going to be 0.010. This will be plus x plus 2x, so x, and 0.010 plus 2x. Well, now we can put all of that into the expression. Since I'm running out of room over here, I'm going to start down here. 9.8 times 10 to the negative 9 is x times 0.010 plus 2x, and then that quantity squared. Just like what I showed you on the PowerPoint, we're going to neglect 2x there. And if you think that's weird, just wait till we get to the next problem. That's going to be fun. All right, and so now we get 9.8 times 10 to the negative 9 is equal to x times 0.010 squared. So we're almost done with this one. We'll solve that for x is equal to 9.8 times 10 to the negative 9, and we'll divide that by 0.010 squared. Okay, and so now we just got to punch that into our calculator. In fact, you could probably figure it out. That number on the bottom is going to be 1 times 10 to the negative 4. So this should come out to 9.8 times 10 to the negative 5. But I know better than to do this in my head and not punch it in the calculator. So divided by 0.010 squared. And we'll get 9.8 times 10 to the negative 5 molar. And as I mentioned, x is equal to the molar solubility. So that is our molar solubility in 0.010 molar iodide ion. Pretty cool. Well, the next thing we want to do is we want to look at this one. We've got lanthanum fluoride. And for lanthanum fluoride, let's go ahead. I'm going to write out the reaction up here. So I grabbed the wrong one there. So lanthanum fluoride solid. It dissociates to some extent to give us the lanthanum ion. And here our lanthanum ion is plus 3. And then 3 fluoride ions, AQ. And that means that our KSP value, or our KSP expression for that, is going to be the concentration of lanthanum ion times the concentration of fluoride ion cubed. Okay. And we're going to need the value. So I'm going to go over all right, I don't know why it's beeping at me like that. We'll look up lanthanum fluoride here. Lanthanum fluoride 2 times 10 to the negative 19. So 2 times 10 to the negative 19. All right, now that we've written out that expression and the constant, we are going to set this up as a concentration table. So since I've got the equation written right there, I'm just going to put the ice table directly underneath. So the concentration of lanthanum in pure water is 0. Concentration of fluoride in pure water is also 0. This will be plus x, and this will be plus 3x. So that will give us our values in terms of x that we can put into this expression. So that gives us 2 times 10 to the negative 19 is equal to x times 3x cubed. So x times 3x cubed. All right, so we're going to have x times x cubed. That's x to the fourth. And we're going to have 3 cubed. And be careful. Don't get tricked on this. Don't get tricked on this. 3 cubed is not 9. 3 cubed is 27. So that's going to come out to 27 times x to the fourth. So 27x to the fourth. So x to the fourth is going to be equal to 2 times 10 to the negative 19 divided by 27. So we will enter that into the calculator and take the cubed root, or not the cubed root, the fourth root. So raise it to the 1/4 power or raise it to the 0.25 power if you want to write it out that way. So x is going to be that value. So we'll do 2 times 10 to the negative 19, and we want to divide that by 27, and that gives us that quantity. But now we want to raise that to the 4th power, or to the 0.25 power, and we'll get 9.3 times 10 to the negative 6 molar. Well, that is the molar solubility. And if the question were asking for molar solubility, we'd be done. But here it's asking for grams per liter. Well, this is moles per liter. That's grams per liter. And so we need to multiply this by the molar mass. Now, I just so happen to have the molar mass because I've solved this problem already. So we'll do 9.3 times 10 to the negative 6 moles per liter. And we're going to multiply that by the molar mass, and our molar mass is 195.91 grams per mole. Now, just so everybody is 100% clear where I'm getting this number, I took lanthanum, and lanthanum is right there. So here is lanthanum. So I took lanthanum, and then I took 3 fluorides, which are over here. So there is the fluoride. I took 3 of those fluorides and added those all together, and that gives me 195.91. So when we multiply that out, that gives us a value of 1.8 times 10 to the negative 3 grams per liter. Now, one last thing that I want to do before we declare victory here is I want to round to the proper number of significant figures. And since our KSP value up here only has one significant figure, then technically we only have one significant figure here. So I'm going to go ahead and just call that 2 times 10 to the negative 3 grams per liter. And that is our solubility in terms of grams per liter. Okay, let's do the next one. So here we've got 0.010 molar Kf. So 0.01 molar Kf. So our common ion is the fluoride ion. So we'll have initial change equilibrium. Lanthanum, there's no lanthanum in the potassium fluoride solution, but our fluoride ion concentration is 0.010. We'll do plus x and plus 3x. So x and 0.010 plus 3x. 0.010 plus 3x. Now we can put all that into our expression. So 2 times 10 to the negative 19 is equal to x times 0.010 plus 3x cubed. Now, previously you saw that we neglected x, and then in the last problem we neglected 2x. Well, move over, Bacon. Here we go. We're now going to neglect 3x. All right, so we're going to neglect 3x. And when we do that, we're going to end up with this. So 2 times 10 to the negative 19 is equal to x times 0.010 cubed. That means that x is equal to, let's see, 2 times 10 to the negative 19 divided by 0.010 cubed. And then when we evaluate that, so I'll do 2 times 10 to the negative 19, and we're going to divide that by 0.010 raised to the third power. And that number comes out to 2 times 10 to the negative 13. So 2 times 10 to the negative 13 molar. Well, that is our molar solubility. Again, we don't want molar solubility here. We want solubility in terms of, we want it in terms of grams per liter instead of moles per liter. So we'll just take that number, the 2 times 10 to the negative 13 moles per liter, and multiply by our molar mass, which was 195.91 grams per mole. We'll see moles cancel out. And then that's going to give us, times 195.91, it's going to give us 3.9. So 3.9 times 10 to the negative 11 grams per liter. Now, one last thing we're going to do is, again, there's only one sig fig here in that equilibrium constant, so we're going to round that to 4 times 10 to the negative 11. So we'll call it 4 times 10 to the negative 11 grams per liter. Well, you can see by having fluoride as a common ion, we were able to decrease the solubility by 8 orders of magnitude. It went from 10 to the negative 3 down to 10 to the negative 11. I can't emphasize just how huge of a change in the solubility that is. That's a really big deal. Okay, well, now our common ion on this part is the lanthanum ion. So again, we'll write out this. So initial change, equilibrium. Our initial concentration of lanthanum is 0.050. For fluoride, it is 0. Do plus x, so 0.050 plus x, and this will be plus 3x. So now we'll put it into our expression. 2 times 10 to the negative 19 is equal to 0.050 plus x times 3x cubed. Okay, we will neglect that x, as we are so fond of doing. And when we neglect that x, we will get 2 times 10 to the negative 19 is equal to 0.050. And then we'll go ahead and compute that. 3 cubed is 27, so we'll put 27x to the third. So now we've got x cubed is equal to 2 times 10 to the negative 19 divided by 0.050 and 27. All right, so 2 times 10 to the negative 19 divided by 0.050, and we'll also divide that by 27. And then we want to take the cubed root. So we're going to raise that quantity to the 1/3 power, so I'll put 3 to the negative 1. And that gives us 5.3 times 10 to the negative 7 molar. And that is our molar solubility. So that's our molar solubility. Again, we need to take that number and multiply by the molar mass. So 5.3 times 10 to the negative 7 moles per liter. multiplied by 195.91 grams per mole. And when we multiply that out, so I'll just leave what's in the calculator times 195.91. Make sure I wrote the right number down there, 195.91. And then that's going to give us 1.0 times 10 to the negative 4 grams per liter. And of course, we're going to round that to 1 sig fig. We're just going to call it 1 times 10 to the negative 4 grams per liter. And that is our solubility for that one. All right. Well, before we move on, and I'm just going to mention this, before we move on to the next factor that affects solubility, which is pH, we're going to stop the video because we're at 45 minutes, and I like to keep these less than an hour. So we'll start up the next video with that.